RL variable capacitor circuit. The RLC series circuit shown in figure has an AC voltage source Vin, which is amplitude Vin cosine omega t, where Vin is the input voltage amplitude and omega is its angular frequency. The values of the resistance, inductance, and capacitance of the components are R, L, and C. The capacitance is variable. The output voltage is V out cosine omega t plus theta. Part A, what is the output voltage amplitude? So in this circuit, let's first note what we know. The input voltage Vin as a function of time t is given as the amplitude Vin cosine omega t. The output voltage, which is the voltage taken across the capacitor, is the output voltage amplitude V out cosine omega t plus theta. The current in the circuit is the input voltage amplitude divided by the impedance of the circuit. The resistive reactance is R, inductive reactance is omega L, capacitive reactance is 1 over omega C, and the voltage in the circuit, basically the voltage across the resistor and capacitor and inductor, add up to the input voltage. So if you write this as a differential equation, the current multiplied with the common current that flows in the series circuit, IR, plus the voltage across the inductor, L di dt, plus the voltage across the capacitor, which is 1 over C integral I dt, is equal to the input voltage, Vn. So that means that these three phasors, the voltage phasor for the resistance voltage, that of the inductor voltage and capacitor voltage would add up to the input voltage phasor. And as a result, we are given that the output voltage V out is the output voltage amplitude, which is the current amplitude I divided by omega C cosine omega t plus theta, which is equal to 1 over the capacitance integral I dt. So we can see that the voltage across the current that flows through the circuit as a function of time is C dV out dt or C dVc dt. So if I calculate this, this will be I over omega. Then I have minus omega sine omega t plus the angle theta. We can see that these omegas will cancel out and we will be left with I cosine omega t plus theta plus pi over 2. So let's see if that works. Cosine omega t plus theta, cosine pi over 2, that's 0, minus sine omega t plus theta, sine pi over 2, that's going to be minus sine omega t plus theta. So minus sine omega t plus theta is cosine omega t plus theta plus pi over 2. So that works. Okay, so we reached the final expression for the current. I of t is equal to the amplitude I cosine omega t plus theta plus pi over 2. Now what is the voltage across the resistor VR? It is the current amplitude multiplied with resistance. It's going to be in phase with the current phasor. Cosine omega t plus theta plus pi over 2. And if we look at the voltage across the inductor, VL, it is L di dt. That is equal to minus I omega L sine omega t plus theta plus pi over 2, which can be written in terms of cosine as VL is equal to I omega L cosine omega t plus theta plus pi. So let's see how that works. We have cosine omega t plus cosine theta plus pi over 2 sine pi over 2. So cosine pi over 2, which gives us 0, minus sine omega t plus theta plus pi over 2 sine pi over 2, which gives us this minus sine omega t plus theta plus pi over 2. So we have found the phase relationship between the inductor voltage, resistor voltage, capacitor voltage, and the current that flows through all of these circuit elements at the same time. All right, so this phasor equation is basically the following. If I write for the resistor voltage, it's IR cosine omega t plus theta plus pi over 2. Then I have the inductor voltage I omega L cosine omega t plus theta plus pi. And then I have the capacitor voltage plus I divided by omega c cosine omega t plus theta. And this must be the total voltage. So basically, I've looked at VR, VL, and VC here. So this is plus minus VR, plus minus VC, plus minus VL. And all of these voltages will add up to the input voltage in this loop. So this is my KVL loop here that I'm considering. So that's the Kirchhoff voltage law equation that I have just written here. This is equal to the input voltage, which is input voltage amplitude cosine omega t, and which is nothing but the current amplitude impedance Z cosine omega t. So I can see how the phasors should work here. So if you consider the input voltage is cosine omega t, has 0 phase, so cosine omega t. The capacitor voltage makes an angle theta with respect to this voltage, so it's at an angle theta. And then with respect to the capacitor voltage, omega t plus theta, I have plus pi over 2 for the resistor voltage and plus pi for the inductor voltage. Now you can see that in this phasor diagram, when you add these three phasors, they would not add up to V in this manner. So if you draw it this way, it doesn't make sense. So we realize that the theta given in this problem must be less than 0 degrees. So it must be a negative angle. So if theta is a negative angle, then I would have omega t plus theta I over omega c. The capacitor voltage phasor would be pointing in this direction. Then if I add 90 degrees to it, this would be the resistor voltage phasor, and this would be the inductor voltage phasor. And in this case, you can see that these three phasors can add up to the input voltage phasor. So I have discovered that theta must be negative. Now, what is the corresponding impedance here? So 1 over omega c minus omega L and R would be the two sides. So I can find the impedance Z is equal to omega L minus 1 over omega c parentheses squared plus R squared square root. The input current amplitude, the current amplitude would be the input voltage amplitude divided by the impedance Z. So I can find this to be the input voltage amplitude V in omega L minus 1 over omega c parentheses squared plus R squared is equal to square root. So let me note here that this is the inductor phasor, voltage phasor, this is the capacitor phasor, and this is the resistor phasor, and this would be the input voltage phasor. So this is a phasor addition process, as you can see in this diagram. Now that I have found how to write the input current amplitude, I can write the output voltage amplitude. The output voltage is the current amplitude I, divided by omega c, the capacitive reactance, multiplied by the current. So this would be V in divided by omega c divided by omega L minus 1 over omega c parentheses squared plus R squared, all inside this square root. So that's the answer we're looking for in part A of the problem. What is the output voltage amplitude? What is the phase angle theta of the output voltage? Now, as you can see in this phasor diagram, I have found out that this angle theta must be negative, and tangent of this angle will be given by the resistive reactance XR divided by XC minus XL. So noting that this angle is negative, so let's start out by checking the tangent of the angle from the phasor diagram. Tangent theta is minus XR over absolute value of XL minus XC, because I know it has to be negative, and tangent minus theta is minus tangent theta. So this comes from my discovery that theta is less than 0 degrees. So if I do that here, it is minus R divided by absolute value of omega L minus 1 over omega c So this gives me the final answer for theta. theta is then minus tangent inverse of r divided by absolute value of 1 over omega L minus it's omega L minus 1 over omega C and I can make sure that this is going to be a negative angle with this expression. I know that tangent is an odd function because sine is an odd function. Sine of minus theta is minus sine theta, but whereas cosine of minus theta is cosine theta. Cosine is an even function. So theta is minus tangent inverse r over 1 over r over omega L minus 1 over omega C in absolute value. So this comes from this phasor diagram basically. You can see if you plot these phasors like this, it's xc minus xl and r. It's going to make a right triangle to determine the z value here. So basically in this diagram, what I have done here is I have a phasor here which is xc minus xl, and here I have xr, and the impedance z will be due to the addition of these two phasors, so this will give us z, and that will be the angle theta here. So this is 90 degrees. From this phasor diagram, I can determine the angle. Let's move on to part C. What is the value of theta at resonance? So when do we achieve resonance in an RLC circuit? So in part C, we have the resonance condition. So if the resonance condition is satisfied, we have omega L is equal to 1 over omega C. That means the circuit behaves purely resistive. All right. So if omega L is equal to 1 over omega C, theta is then minus tangent inverse of infinity. So when do we obtain infinity for the tangent of an angle? That happens at pi over 2. So it's sine pi over 2 or cosine pi over 2. Cosine pi over 2 is 0, sine pi over 2 is 1. We obtain infinity, which means theta must be equal to minus pi over 2 at resonance. That's the condition we find for the phase angle. Part D, if the resistance is 100 ohms, inductance is 1 microhenries, input voltage amplitude is 10 volts, what value of C would result in a resonance frequency of 100 kilohertz? Let's move on to part D. Now, we're given the resistance 100 ohms, inductance 1 microhenry, input voltage amplitude 10 volts. The resonance frequency is to be 100 kilohertz. The resonance frequency, angular frequency, is 1 over square root of LC, which is found from this equation. Omega square is 1 over LC. So omega resonance is 1 over square root LC. So LC omega resonance square is equal to 1. Then the capacitance, because this has a variable capacitance, capacitance will be 1 over L. For omega resonance, we will substitute 2 pi Fr, so it's 4 pi square F resonance square. If we substitute the values for the inductance, 10 to minus 6 Henry, 4 pi square resonance frequency 100 kilohertz, 110 to 3 parentheses squared. So this gives us the final answer for the capacitance to be 2.53 microfarads. All right, and let's move on to part E. In that case, what would be the output voltage amplitude at resonance? The output voltage is going to be equal to the input voltage divided by omega resonance RC. So we have V out is equal to V in over omega C. This term is equal to 0, so we would have V in divided by omega RC equals V out. So this is what we see from part A. So if I substitute the numbers here, this will give me V out is equal to 10 volts divided by omega resonance 2 pi 100 kilohertz, 100 times 10 to 3. And then I have resistance 100 ohms, 2.53 10 to minus 6 farads. So that's microfarads. And that gives me the final answer for the output voltage amplitude to be 63 millivolts. That's the answer to part E of the problem. All right, so in this case, we have an RLC series circuit, but the capacitor has variable capacitance. So we can show that by putting an arrow here. It has variable capacitance. The input voltage is V in cosine omega t. Output voltage is V out cosine omega t plus theta. Looking at the relationship between the current, the common current that flows in the circuit, and the voltages, I have realized that the voltage across the resistor is IR cosine omega t plus theta plus pi over 2. The voltage across the inductor is I omega L cosine omega t plus theta plus pi, and the voltage across the capacitor is I over omega C cosine omega t plus theta. Showing this in a phasor diagram, we realize that theta cannot be positive. If theta is positive, these phasors would not adapt to the input voltage phasor, as would be required by the Kirchhoff voltage law. So the theta must be negative. If theta is negative, then you would have with this relationship, this is at angle omega t, this is at omega t plus theta plus pi over 2 plus pi. So we have the inductor voltage phasor. So you can see that 1 over omega c minus omega L would be here, and R would be here. So these would add up to give us the impedance of the circuit Z, making an angle theta with respect to the x-axis, which is this axis in this case. Okay, so the impedance of the circuit is then omega 1 over omega c minus omega L parentheses squared plus R squared square root, and the current amplitude is V in divided by the impedance. So V out is I over omega c, so V in over omega c divided by the impedance of the circuit. Now this angle theta, with respect to the x-axis, tangent of the angle is xr divided by xl minus xc, but the angle must be negative, so to ensure it's negative, I put a minus sign here, minus xr divided by absolute value of xl minus xc. From this we can obtain theta. If we have the resonance condition satisfied, omega L is 1 over omega c, theta becomes minus tangent inverse of infinity, which means the angle is minus pi over 2. Given these values for RL and V in and resonance frequency, the resonance angular frequency is 1 over square root LC. That means we have theta is equal to minus pi over 2, and that also means V out is V in over R omega C, because this term would be 0. So from this, I can calculate the value of capacitance to have a resonance at 100 kilohertz, which is 2.53 microfarads, and using this equation at resonance, I obtain V out is equal to V in divided by omega RC. So substituting these values, we obtain 63 millivolts.